So I'm going to give a general review of discoveries and some suggestions for future progress on magnetospheric imaging. I'd like to thank Rick and Andy for inviting me to talk about this. I know it's kind of madness to consider doing a review talk in 20 minutes, but we'll see how that goes. I also want to point out that I'm going to be talking about four main topics: plasmaspheric imaging, ring current imaging, Saturn's plasmasphere, it sounds like a Jeopardy category list, and system-level imaging and what the future holds for imaging and magnetosphere throughout the solar system. Now, I'd like to state a disclaimer that this is viewed through a very narrow lens of things that I have actually worked on. So this is by no means meant to be a comprehensive review, but I hope it gives a sense of the flavor of one person's perspective of what magnetospheric imaging has done for us. So first I'd like to talk about plasmaspheric imaging, which is the majority of what I've worked on this topic. I have personally seen this amount of progress that we've experienced. We've confirmed some very basic theoretical paradigms for the inner magnetosphere. We have revealed, or in some cases made obvious, what models had told us were global patterns of behavior, confirmed the profound importance of MI coupling to the inner magnetosphere, and I'll be hitting that thread many times in this talk because this is an MI coupling workshop, and then helped refine our models to I think a pretty credible level of accuracy, as I'll try to demonstrate later. So some of the earliest results. This is my favorite Plasmapause profile plot of OGO5 data because it really shows this just basic idea that when Kp is high, the plasmapause moves inward. And also it shows the subglobal and mesoscale and fine scale structure that the plasmapause density profile can be highly structured. This is just an example of that type of structure, and that's really important for talking about. I'm going to be focusing on the things that magnetospheric imaging has done for us, but we still have a long ways to go before we really understand this problem. Now, here is a sequence from late June through early July 2000 of image EUV images. And, well, they say you always remember your first kiss. I remember my first plasmasphere image. It was better than my first kiss, actually. So what this series of images shows is that there is a repeatable pattern of global behavior. It's not just that the plasmapause moves in when Kp is high and moves out when Kp is low. It's that there is a global morphology that really provides, I think, a really remarkable and reliable paradigm for interpreting not just images, but for reinterpreting decades of in situ observations. So these two things go together, and I hope that comes across in what I'm about to show, that the in situ data provides very localized measurements of ground truth. That's what's really happening, but it doesn't show the big picture. And if you can connect the big picture to the in situ measurements and interpret them in a way that lets you really see a systems level view, then I think you've made enormous progress. And I think we have done that to some degree. So one of the earliest modeling papers for the plasmasphere, there were several other really good ones. My favorite is Grabowski. Jim Birch was talking about this morning, how this paper predicted the formation of plumes. This is a simple test particle simulation subject only to a uniform dawn-dusk convection electric field and a co-rotation. Not an offset dipole, just a simple co-rotation electric field or electric potential. And that plumes form in response to enhanced convection. This very, very simple paradigm can get you a long way towards interpreting the global images. Now, this is the reason I'm using my computer, just for these two movies here. So this is the same model that Grabowski used, uniform convection electric field, co-rotation. It's just in color. It's like Frank Capra movies, colorized or something, because we know the plasmasphere is green, thanks to image. So this up here is the convection electric field strength going from like 0.1 to 0.5 millivolts per meter. That's, I think, very close to the same convection strength that Grabowski used in his model. And this is the open, closed, equipotential boundary. And when this thing moves inward, you get erosion. So we're starting with a circular plasmapause and just running it. And this paradigm really explains erosion. You don't need SAPs. You don't need anything else. All you need is solar wind-driven convection, global convection, and you get a plume. Now notice the plume gets narrower and narrower with time. That happens every time you have sustained convection. You start with a broad plume from the onset of convection, and you end up with a narrow plume. If you let the convection be steady for over a day, of course you'll get closer to this teardrop, which never, ever, ever happens. The solar wind always changes before that, and here's an example of another simple simulation showing you increase the convection, then you decrease it again, you're narrowing, but suddenly now the plume is rotating and wrapping. That happens in some form or another. These phases of the plasmasphere happen for every convection event that I've ever seen in global images, and so I think that this paradigm of driving the plasmaspheric erosion in terms of the global morphology and the global pattern, I think it's a really good one. You start with a quiet plasmasphere. You start an erosion event that is an enhanced convection, and both the images and the models say that you have a broad plume across the day side when you first start the convection. That's the 32 tons of material mass that's being eroded. Even for just a couple of L-shell erosion, you're talking about tens of tons of material. You can integrate that from the flux rates that John Foster was talking about, for example, today. Yeah, so for over the overall rate, if you add that all up, it adds up to about, if you go from L of 6 to L of 4, dipole magnetic field lines, uniform density along the field lines, it's about 32 tons. So in this image, note this is the camera cut off here. The plume goes past the camera edge, and we know that because we've looked at simultaneous in situ observations from Los Alamos when we used to have those. And you can confirm that there's a plume where this stuff goes out of the camera view. The plume gets more narrow with time, and then it starts to rotate and wrap when convection decreases. This is a cartoon model with a uniform convection electric field and with a ridiculously circular initial plasma pause. If you just include realistic initial conditions, which are taken from this EUV image, and propagate that with, in this case, a Wallen-Stern potential, then you get even better agreement. I think this is pretty credible, and this doesn't even include MI coupling. To really do better than this, you've got to include MI coupling, because I think it's that which really determines the subglobal, the mesoscale structure of the intermagnetospheric electric potential. It's the region 2 current system, it's the ring current, it's all of these things that during storm times are very important. So before I get into MI coupling, I just wanted to reiterate this point that these images that show very clearly plumes, this is in an early recovery phase just after a substorm for this particular image, showing the plume is just starting to rotate and wrap. This is a model prediction from early recovery phase. Here's just a nominal sketch of what an orbit might be passing through here, and this images and its agreement with the global paradigm suggested by the models, the Grabowski type of model, or any model that has convection and co-rotation as the basic drivers. So it's a really good way to provide a context for these in situ observations. This is the trajectory of IC1 in late 1983, and this is the detached plasma region that is just the cross-section of a three-dimensional structure. But notice also that although this global paradigm, which was sort of refined using these images, there's so much more going on here than just this simple laminar curve. Look at all this structure in the density profile. How much of that is from previous structure that's been distorted and stretched and like taffy by the structure in the convection electric field? And then look at all this at large L values on the day side, getting out towards the magnetopause. All of this plasma, what is that? Where is that coming from? And these are the things that we still don't know. So there's a lot more progress that needs to be made, but I think it's a great thing to be able to look at these observations and just on a global scale be able to say, okay, we think we know what's going on at least globally. Let me talk a little bit about MI coupling. I have a few slides on this. The first one, John Foster has already introduced, so I won't belabor it. It's suborbital polarization stream, or SAPS. It's a convection enhancement that I think is really driven by the ring current. You have a partial ring current here. This is a three-quarter view of a ENE image that I put into a cartoon. And you've got the region 2 current system coupling to the ionosphere, and its coupling with connecting with the region 1 current system produces more or less radially pointed electric field It's strongest in the dusk side, although it extends around to all local times. It's strongest in the dusk side. So the zero order, you're looking at a dusk side a westward flow channel that enhances the solar wind-driven convection. The solar wind-driven is the global part, which you could model simply as a uniform convection electric field and get reasonable agreement with data. But to really refine the agreement with the imaging observations, you really need to include this MI coupling, this ring current ionosphere coupling effect, the effect of the region 2 current system. This is a simulation of the plasmasphere that was run for two different versions of the model, one with no SAPs, one with SAPs, run for 2 months of EUV observations. So the black dots are the EUV, the red is the model with SAPs, the blue is the model without SAPs. And let me just take a close-up of one of these and then generalize. What the dusk side flow enhancement, it's strongest on the dusk side, it's really on the entire night side. What the dusk side flow enhancement does is it pulls the model plasma pause in from where it would be for a no MI coupling. When you add MI coupling, you pull the plasma pause in and it lines up with the model much better. It lines up with the observations much better. Now that's the general case in these examples here, that you get better agreement. And if you don't believe me, you can bin the observations by KP, and then you can see that the plasma pause versus KP curve, the blue curve without SAPs, is offset from the true curve, which is the image EUV observations, which are the black, and the red does a better job. You can look at the difference in the the two respective models from the EV observations here, and you can see that it's much closer to 0 for these bin by KP values. So, taking a model like that, now that we don't have image EUV anymore, and applying it to a data set where we really can't check what the global plasmasphere is doing, but try to interpret the in-situ observations using the model. This is a plot showing, here's one of these model 2D plasmaspheres. We've got a wrapped plume. This plume is about 30 hours old. It's been rotating and wrapping for about 30 hours. In the model, these plumes will really last forever unless you can design a means of snipping them off, but I've never been able to design an algorithm that does that. There are 4 plots here. 2 of them are the in-situ wave-derived density from the emphasis instrument on RBSP, the Van Allen probes. This is A, and this is RBSP-B. Notice there's a little detached plasma region. It's very low density because it's well after the onset of the erosion event, so this density has dropped significantly. And in the model, you see the virtual RBSP-A satellite, the virtual RBSP-B satellite. Now, there's not perfect agreement with where you would call the 40 per cc threshold in the emphasis data, which is the lower threshold of sensitivity on average of the image EUV instrument, or was. But you notice that in around the right area, the simulation predicts that there's a 30-hour-old plume right where you see this really old, that's really tenuous but detached plasma region. So I think that's pretty good. If you look at versus time, plasma pause L values of the model are in dashed lines, blue and red respectively for RBSP A and B, and then the observations are blue and red but solid lines, and just plot versus time and look at how the model does. On average, it's disagreeing from the observations with the virtual spacecraft versus the real spacecraft observations of the 40 per cc plasma pause by about 0.4 RE. I think that's pretty darn good considering how, pardon me for saying this, how crappy my model is. I think it's a really very overly simplified model, and yet with just such a simple model, you can do this well. You can do even better with one of the self-consistent electric field models, or any of them that they're working with. You can do a lot better job than this. And here's an example of a better model. This is an empirical model from the Rice University magnetospheric specification model, kind of the baby brother empirical version of the truly self-consistent RCM. And it includes our ring current ionosphere coupling. This is a plot intended to show a reverse 2-cell convection pattern produced by shielding. This was an eye-opener for me when I was looking at image EV observations early in the mission. So you've got this region 2 current system, and it's you've got the partial ring current connected by the region 2 current system, and the coupling produces this reverse 2-cell convection pattern that opposes the generally sunward 2-cell convection pattern driven by the solar wind directly. So what does this do? This was, the model predicts that this would drag plasma out. This is with co-rotation removed. These are the equipotentials with co-rotation included, and the color is log of density. So red is high density and green is lower. This two-cell convection pattern is actually dragging plasma out and forming a shoulder-like feature. This model was run specifically to address these observations. A plasmaspheric shoulder, which was discovered by IMAGE, although there was an early paper by Don Carpenter that really predicted this in a schematic picture from looking at Whistler observations. So discovery and explanation coming from the synergy between global images and global models. And I should also point out that the great value of having good mentors. I ran this simulation as a postdoc and really didn't understand what I was looking at. It was Dick Wolf's insight. He said, oh yeah, it's this is what's happening, and so I wrote up the paper, but really the insight was Dick Wolf's. So I think it's appropriate at a meeting like this to point out the importance of having somebody there to hold your hand and point you. Go ahead, you can do this. Okay, so work on image EUV continues. These images we stopped receiving them in 2005, but people are still working on them. This is a wonderful, wonderful data set. There were a series of 2 papers that are just submitted by Nakano et al. I'm revealing myself as the reviewer here. It's a wonderful paper, and these results were presented at Fall AGU as well. Now, this technique does 2 things. One, it produces the inverted helium density from EUV using a Bayesian inversion technique, which I think is a great improvement over prior attempts to invert the EUV images. And they validate it using a model distribution, which I think is a wonderful way to validate it. You know what the answer is in the model. Things that need to be done is add sunlight contamination and real instrumental effects, but I think this is a major step forward. The second thing that Nakano et al.'s work does is looking at electric fields and drifts. And I did a little bit of work, once again, very primitive work here, and looking at the motion of the boundary and getting a 2D electric field. This work uses Kalman filtering technique, which allows you to extract flows from inside the boundary. And here's the extracted red curve for versus the true model electric field, and at L of 3.5. And I think it's doing a pretty good job. So there's still interest in working with these images, even the historical images, because there's still insight to be gained. What's left to study? Obviously, the global picture is only one piece of the puzzle. There's a lot more. And I would say the most important thing that we don't understand is the quiet time plasmasphere. We still have, these are pictures put together by Dennis Gallagher several years ago of various features. And just look at these shapes of the plasmasphere. This is nothing like what any models I've ever seen can produce. And yet this is what's really happening. So there's a lot going on we don't understand. Finally, very fine scale structure in the flow fields. More subtle effects like interchange instability perhaps are working when convection pulls away, like the stars coming out at night when the sun goes down. The plasmasphere is part of an integrated system of coupled self-modifying plasmas, I think is something that is still worth looking at. What do we want? We want higher time resolution to look at erosion timing better. We had 10-minute resolution with EUV on image. We really need better resolution than that to understand how information propagates through the magnetosphere. We need better sensitivity. In order to see that fine-scale structure, low-density plasma on the day side, for example, that you saw in the IC1 data, you need better sensitivity. You also need to see the plume go out to the magnetopause and see its effect on reconnection, so we can answer that question. What effect, if any, does plasmaspheric material have on the day-side reconnection rate? And here's an idea for just a simulated image that we put together, assuming that you had apogee outside the bow shock with a factor of 12 improvement in sensitivity over what image EUV has, and you can see the plume hitting the magnetopause. So that's the sort of thing that we need to do to study that problem. Okay, shifting gears to a couple of examples from ring current imaging. The first here is from the TWINS mission, which I've been working on for several years now. It's 2 spacecraft, stereo ENE imaging, and what do you get from that? One of the most important things you can get from that is determining of global pitch angle anisotropy. So here are 2 TWINS images. In this particular event, which was in April 6, 2010, just around 12:15 to 12:30 UT, the viewing geometry of the spacecraft they were very similar MLT on the day side, but different latitudes. So in these images, the Earth is the black circle, the red dipole field lines are noon, the purple ones are dusk, and we're looking from above the down in in the northern hemisphere down on the northern pole. So there were different MLT, similar MLT rather, and different latitude. Twins 2, which is at higher latitude, on the dusk side, saw half as bright of ENA emissions as Twins 1 at lower latitude. You're sampling the pitch angle. Simultaneous measurements from two directions, you're sampling the pitch angle. That tells you that on the dusk side, you have a pitch angle anisotropy that is higher than on the dawn side, where the ENA intensities are very, very comparable to each other. There's very little change. So you can turn that into a global pitch angle anisotropy map, and this shows a much higher anisotropy on the night side, on the dusk side, than on the dawn side, and that this effect, the red curve is the dusk side anisotropy versus energy in KeV. The blue curve is dawn. Dawn is basically almost zero anisotropy as measured this way, and then there's a slight increase and then falling with energy in the pitch angle anisotropy. So this effect is energy dependent. It gives clues to the mechanism. I still don't know what the cause of this is, and I've worked with several people to try to understand this. This is the sort of information you get from imaging that you can piece together from statistical observations, but I think to really study global dynamics of this type of thing, you really need the imaging to do it. Here's another example from looking at low altitude emissions, which are the ENA signature of ion precipitation. So your twin spacecraft is looking down on this bright emission. It's very bright because the geocorona is much denser closer to the Earth. So it's often the brightest signal in the image. And it's also from an optically thick region of the image. That is that ENAs emerging from these low altitudes are experiencing multiple charge exchange and stripping interactions before they're on their way out. So Bazell et al. Used some simple analytical approximations and produced, I think, a pretty elegant way of converting the ENA pixel averaged intensity to an ion flux. And the result of doing that for this particular study is shown here. That's the yellow data. This is Twins 1 and 2 averaged ions, so taking the ions from all the Twins 1 and all the Twins 2 observations together and binding them together versus energy, you get this spectrum. And this is from simultaneous NOAA observations from very nearby, showing this spectrum. And in terms of absolute ion flux, they agree pretty well. I should point out there are some assumptions you have to make because the pixel size is much larger than what we think is the source region. And so depending on where you assume these emissions are coming from, you get a factor of 10 difference in the twins deduced ion fluxes. So there's still a ways to go, but I think this is a pretty good step forward. If you look at the dependence of the spectra from each pixel in the image at low altitudes, you see this progression here from pretty almost monotonically falling spectra near post-midnight and with an average energy of 18 keV, and then as you get closer to pre-midnight, I apologize if you can't see it, but this is the pre-midnight curve. It's much more sharply peaked, and its average energy is higher, therefore, of 25 keV. So this local time dependence of precipitation, you can actually start to look at the dynamics of precipitation globally this way, where before this technique of thick target analysis was developed, this was sort of the low altitude emission was kind of quantitatively sort of ignored in the image. Here's an example of putting together ENA imaging from IBEX with twins, showing the arrival of a shock and a subsequent substorm. What you're seeing here is before the interplanetary shock. Here is the side view seen by IBEX from the side and outside the magnetosphere, showing low ENA intensity on the day side, and then after the shock, the entire day side lights up. At the same time as this shock arrival, you see in the twins image, the entire ENA image lights up. Some of that is backgrounds from direct particle penetration into the imager. Actually, probably most of that is. But it's still a signature of the entire day side lighting up. And then it takes about 20 to 22 minutes later where you start to see the first precipitation at low altitude. So this is giving information about how energy is propagating through the magnetosphere. You know when the hit happened, because that's when all the images light up. And then it takes that long for particles to start precipitating. And that's energy-dependent effect as well. The most energetic particles are precipitating first. I wouldn't be a complete review of imaging of the ring current without at least showing one thing from image, so I wanted to show this one, which is my favorite example of the synergy between global models and global imaging from ring current imaging. So observation said that there was a peak in the post-midnight MLT sector in the ENE images. And one model, which is running the self-consistent region 2 coupling between the ring current and the ionosphere, reproduces the skewing of the peak. Now, the intensities are not the same, but look at where the peak is. It's post-midnight. Whereas if you use the empirical model, you don't get that answer. And it's this sort of side-by-side comparison where you have global information, which formerly, before imaging, the only way to get global synoptic information was using models. But now you can compare the two together and start to learn something about MI coupling. So the future of this, once again, a wish list. We need higher spatial resolution. One of the things I'm most interested in is the mesoscale structure in the ring current, where you could produce numerous modeling results have shown this. Mike Lamone has shown some of these results. I believe Natasha Buzalakova, who works with Mei-Ching Fock, has shown this as well. Stan Sazigan shows this with RCM simulations, where you have mesoscale structure in the ring current, and each one of those can produce its own little miniature region 2 current system. So your MI coupling becomes so much more dynamic and structured. And of course, higher time resolution to study the dynamics of the day-side boundary region. Okay, a couple of more things I want to say. One is that if you apply the concept of shielding to the Saturnian system, you can gain insight into something that, into some of the observations. Here are 12 Cassini orbits showing a sinusoidal m=1 density pattern with a peak at around 330 degrees SLS3. That's a Saturn longitude system. So that's a global m=1 mode seen in situ from 14 orbits. If you put together over 3 years of Cassini CAPS data, you see this pattern here, a cam-shaped density, where the peak of the most outward thrust part of the cam, the peak in the density, is occurring once again at 330 degrees Saturn longitude system. There's a lobe that goes out to 25 RS, and it's peaked, like I said, at 330. If you, I actually put together a simple model for the perturbations from a circle. Delta L is the perturbation from a circle, and it's perturbation of this circle, L0. So this is a nonlinear function of L0. That is, the perturbation from a circle, the non-circularity, increases as you move outward. That's very suggestive if you look at the theory of interchange instability, which interchange sort of drives everything at Saturn, so it's a natural culprit. If you look at, for example, theoretical papers by Tom Hill, numerical simulations as well show that you have this sort of nonlinear growth. As you move outward, the asymmetry in the density will increase. So it's not necessarily a problem, but one thing that is known from interchange theory is that high M modes will dominate. That is, the system tends to pursue fine-scale structure that is regulated by the width of the density gradient. So this tells you that you expect to see highly, highly structured density, and what you see is that there is an m=1 mode. For that to happen, there has to be, I think, some sort of driving mechanism. So several authors have proposed that there's a global rotating two-cell convection pattern whose throat or outflow region is sort of centered at 330 degrees longitude, and the whole thing's rotating with the planet. Where does that come from, however, is an open question. So we put together a very simple model to study the question of whether or not this two-cell convection pattern produced by shielding at Earth, this idea, and we know it drags plasma out and forms a shoulder because we have very graphic proof of that in the imaging observations. Can this sort of two-cell convection pattern at Earth, known to happen at Earth, could this work at Saturn to get started a global m=1 mode? So at Earth, of course, the ring current injection is occurring on the night side, and then the ions are Grabowski curvature drifting. At Saturn, the whole pattern is rotating around with the planet for many, many hours. So that means if there is a two-cell convection pattern, it's rotating with the planet. So this simple model, which I will scroll through very quickly, you start with a circular cold density, and you initiate a very, very simplified asymmetric ring current, which gives you a two-cell convection pattern. It drags the plasma out, and once that gets started, you turn off the ring current. It doesn't matter anymore. It's 10 times weaker than the interchange potential, which then can produce the observed degree of asymmetry that you see in those CAPS observations in 26 hours or so. So I think it's a plausible mechanism. What do we need to do? I would love to see a Plasmasphere Imager at Saturn. So we could do the same thing we did at Earth with looking at the relationship between the ring current and the plasmasphere, but do it at Saturn. We have global observations of the ring current, but our global picture of the plasmasphere of Saturn is we have to piece it together with some modeling and with statistical observations of in situ data, statistical analysis rather. The last thing I want to talk about here is something that I really would like to see us do, and that is truly global imaging of the magnetosphere, kind of start to finish. The idea here is to put an imaging and in situ observing spacecraft outside the bow shock. So you get in situ solar wind measurements. You're measuring the solar wind input right at the magnetopause. Then you have a dayside boundary imager, which I won't go into the details of, but it uses soft X-ray imaging. And you can see these are simulated images taken from the LFM and feeding into instrument response function and whatnot, and producing these images showing compression caused by this pressure increase in the solar wind, and then magnetopause erosion caused by sustained southward IMF. So there are definite signatures that you can see in images like these. Put that together with an enhanced EV imager where you can actually do timing studies. You can try to make causal connections between what's happening on the night side and with what's happening on the day side, and study the time dependence of the plume intersection with the magnetopause to study feedback with reconnection, and putting together auroral imagers with that whole picture, start to study polar cap area, looking at the MLT location of this cusp precipitation spot. So putting this all together, I think we would have a truly global picture of what happens. You look at the input and study the response of the entire system together. Okay, so what have we, if this very, very myopic and narrow view of magnetospheric imaging, I think still can show that we've confirmed some basic theories, we've discovered new global structures and behavior. We've demonstrated how important it is at a system level and at a local level that you include MI coupling. We've refined our models, I think, to a pretty good way. Even a crappy model can sometimes do a pretty good job. And I think, really exciting, we've provided some universal paradigms to use in comparative magnetospheric physics, which I think is part of what it's all about. Thank you. Uh-oh.
If you had to pick Saturn or Earth?
For what?
A new mission.
Are you with us or against
Oh.
us?
How much money do I have? That's like asking who's your favorite child. But I think really, I think there's, in many respects, what is known about the plasmaspheric Saturn harkens back to pre-imaging days. I think if I had to pick, I probably would pick Saturn.
Good choice.
Did I hear applause there? Did I give the right answer?
Saturn is out at 10 AU. Is there enough EUV photons from the sun? I don't know the density of the plasma you were just looking at. Is there enough EUV photons from the sun to make such a measurement?
It's a challenge.
Actually?
Bill Sandel and I have looked at this, and it's possible. More than just a one-page memo between Bill and me is required to really get a handle on this. We need to do a real study for this, but it's a really good question. But I think it's possible to do, and depending on how you do things, if you're fixed platform, steering or rotating, it makes a big difference. That's part of the increase in sensitivity that you can get by steering. So it's a really good question. It needs to be studied, but you have more ion lines you could look at.
Just a quick question about your twins ENA imaging results that you showed. You certainly convinced me that the ion anisotropy is much larger at dusk than it is at dawn. I didn't catch the sign of that anisotropy. Is it?
Oh, it's more
perpendicular larger than parallel?
It's more of a pancake at dusk than at dawn, which incidentally is opposite to the dependence in anisotropy that you get from statistical analysis. Mick Denton did this with Los Alamos data. Statistical analysis of Los Alamos data shows the opposite dependence, but that's statistical. There are a lot of things that happen globally on a shorter time scale that wouldn't show up in something like that.
Okay.
The global dawn-dusk pitch angle anisotropy? Yes.
I wanted to kind of follow the plume out
and make a tangential point that when this meeting was held 40 years ago, there were still pretty loud voices in the community that were totally skeptical of reconnection.
Well, it's just a big lie.
Existing.
I mean, we all know
And
that.
I think the sort of nail in the coffin of those criticisms is partly the plume going out to the magnetopause, and then our ability to actually observe that there's plasmaspheric stuff outside the magnetopause and solar wind stuff inside of it. You very clearly got
I won't
mixing of the two.
I won't address the you know, the complications that arise from bucking the paradigm. I will say though that there's enormous value always in re-examining the most fundamental views. If you're smart enough, I personally am not, but many people are, to look at these sorts of things at a really, really basic level.
Everybody gets to think it through, right? Okay, so time to move on.